Ever find yourself standing by the tracks, a train just flies by, and you think, how on earth do they stop these things?
Yeah, it's incredible, isn't it?
Well, that's what we're looking at today. Diving deep into the world of train braking and all those forces working against them every time they leave the station.
It's easily forgotten.
Yeah.
The sheer engineering that goes into just getting a train moving and then
Yeah.
bringing it to a halt safely, the physics involved, especially when you talk about braking distances, it's really something else.
Absolutely. I mean, it's not like hitting the brakes in your car. We're talking hundreds of tons of metal hurtling down the tracks. So, how do you stop something that massive? I mean, what kind of things influence how much distance a train needs to come to a complete stop?
Well, speed obviously plays a huge role, just like with your car. But with trains, you've got to factor in the massive weight they're hauling. That's a real game changer. A freight train, fully loaded, that's going to need a much longer distance to stop safely than a passenger train. And then, of course, you got to think about the terrain.
Yeah, those hills and valleys can't make it easy.
Exactly. Going uphill, sure, that helps to slow you down, but going downhill, well, gravity starts working against your brakes. Means you need even longer stopping distances. And then on top of all that, you got the technology itself, the braking systems. Over the years, we've seen them evolve drastically, from
Yeah.
the early days of shoe brakes to the much more modern disc brakes you see on trains today.
And talking of braking systems, our sources mention a whole bunch. Air braking, electropneumatic braking, even something called electromagnetic braking. It's way more complex than I realized.
Oh, it's a fascinating area of engineering, really.
Yeah.
Each system has its own, quirks, advantages. Let's take air braking, for example. Been around for ages.
Hmm.
Relies on changes in air pressure to actually engage those brakes. Then you've got electropneumatic braking, which uses electrical signals for much faster, more synchronized braking, especially important when you've got all those train cars all needing to brake together.
Right, makes sense. And what about this electromagnetic braking? Sounds seriously high tech. Uses the rails themselves to stop, right?
You got it. Electromagnetic braking uses electromagnets to generate friction directly on the rails. This gives much more controlled and efficient braking, especially at high speeds. But the really exciting development, in my view, is electrodynamic braking. This system actually harnesses the energy generated by the train slowing down.
And that's clever. Turning a negative into a positive. You're saying it actually uses the act of braking to generate energy.
Precisely. It converts the train's kinetic energy, the energy of motion, into electricity. This electricity can then be used to power the train's onboard systems, or it can even be fed back into the power grid. So that's what I call making trains even more sustainable.
Wow. So we've got all these different types of braking systems, each with their own pros and cons, but I imagine when it comes to safety, there's no room for error. Are there specific rules or standards that all these braking systems have to meet?
You're absolutely right. Safety is paramount. And that's where things get really interesting, particularly here in Europe. To ensure that everything runs smoothly across all the different countries and their rail networks, we have these comprehensive European specifications for train braking.
European specifications. Okay. So it's like a kind of universal language for train brakes across the continent.
You could say that, yes. They ensure a train from, say, Spain can seamlessly operate on railways in Germany, all while maintaining those high safety standards. It's all about what we call interoperability.
Interoperability. Got it. So everything works together, no hiccups. It sounds like these specifications cover a lot of ground. What are some of the key things they focus on?
Oh, they're very thorough. They cover things like braking performance in detail, considering factors such as braking power, the train's mass, the speed it's traveling at, even something called running resistance. I'll come back to that a bit later on.
Wow, sounds incredibly detailed. So these specs make sure a train can brake safely, whatever the terrain, right? From mountains to those long stretches of flat track.
That's the idea. It has to cover all eventualities. A train climbing a steep mountain pass in the Alps or cruising through the French countryside needs to be able to brake effectively and within a safe distance. And a huge part of that is what we call adhesion.
Adhesion. So that's the grip between the train wheels and the rails, right? Kind of like when your car tires lose traction on wet roads.
Perfect analogy. Just like with your car, rain, snow, even leaves on the tracks can significantly reduce adhesion, which in turn impacts how effectively a train can brake. And these European specs take this into account. They're not just about the brakes themselves, but all those external factors too.
So it's about making sure those brakes work no matter what, no matter the conditions. Do these specifications also take into account different braking situations, things like emergency braking as opposed to just slowing down?
Absolutely. They cover everything, from
Hmm.
the main braking functions during normal operations, such as service braking, all the way to the emergency brake system. They also mandate that train drivers have systems which allow them to constantly monitor the status of the brakes from their driving position. That way, they always know what's going on and can react quickly should they need to.
Wow, a real safety net. Okay, so moving on, our sources also mention those invisible forces you talked about, the ones trains have to overcome every time they move. These resistances, it's incredible when you think about it, this constant battle against unseen forces.
It's a fascinating aspect of train dynamics. I mean, we often take for granted the sheer energy required to move these huge machines, but these resistance forces are always there, working against them, regardless of the weather, the terrain, anything.
And you mentioned a few different types: running resistance, curve resistance, grade resistance, and something called inertial resistance. Let's start with running resistance, what actually contributes to this force that's working against the train.
Sure, running resistance is essentially a combination of mechanical and aerodynamic forces. Think of it this way. Even on a perfectly straight and level track, a train still needs to overcome friction and air resistance.
So even with no hills, no curves, there's still this kind of drag the train has to constantly fight against.
Exactly. Things like the weight of the train itself, the condition of the wheels and the bearings, even how smooth the tracks are, all play a part. This is what we call mechanical resistance. And then as the train gains speed, you get increased aerodynamic resistance, which is essentially the force of the air pushing back against it.
Makes sense. The faster you go, the more you feel that air resistance. Our sources talk about the formulas engineers use to calculate this resistance. It's not simple math, is it?
It really isn't. These formulas take into account so many variables: the train's shape, its size, the type of cargo it's carrying, even how many cars are in the train. Interestingly, different railway systems around the world actually use slightly different formulas based on their own research and operating standards.
So really, so for instance,
Well, American and European railways, for example, they both have their own ways of calculating running resistance, which reflects the specific conditions and priorities of each network.
so each railway system having to make tiny tweaks to the formula based on its own unique challenges and experiences. It just goes to show how much thought goes into understanding these forces.
Absolutely. And these calculations, they have real-world implications. They influence things like fuel efficiency, how trains are designed, even scheduling. But let's move on to another type of resistance, curve resistance.
From what I understand, that's all about the challenges of getting around those bends in the track, right? It can't be easy for something as large as a train to navigate curves.
You'd be surprised. Well, you wouldn't be surprised. It's exactly that. Imagine a train going at speed, and suddenly it needs to go around a tight curve.
Hmm.
Naturally, it wants to keep going in a straight line. That's inertia at play. But the tracks force it to change direction. This creates what we call curve resistance.
So the tighter the curve, the more resistance.
Exactly. It's a big factor in train design and operation. It's one of the reasons why high-speed lines often have much gentler curves. Minimizing curve resistance is essential for maintaining those high speeds.
Like designing a roller coaster, smoother curves equal more speed. Okay, so what about hills? Going up and down must create a whole other set of resistance challenges.
Absolutely. This is what we call grade resistance, which is basically the force of gravity acting against the train. Think about riding a bike. Cycling uphill is much tougher than on a flat surface.
And cycling downhill, well, gravity lends a hand. I imagine it's the same for trains.
Exactly. When a train is traveling uphill, it has to work against gravity, which is grade resistance. Going downhill, gravity assists its motion, meaning it can coast easier and achieve higher speeds.
All about that balance of forces. We haven't talked about inertial resistance yet. What's that?
So inertial resistance is all about getting a train moving
Hmm.
and also dealing with those changes in speed. Basically, objects at rest, they like to stay at rest, and objects in motion like to stay in motion. This is inertia. So to get a train moving from a standstill, you need to overcome its inertia. It's that initial resistance to movement.
That initial push to get things going. And does inertia also affect things when a train speeds up or slows down?
Exactly. It takes a lot of force to get a heavy train moving from a standstill. And that same inertia comes into play when accelerating or braking. You know that feeling of being pushed back in your seat when a car accelerates quickly?
Yeah, I do.
That's inertia. And with something as heavy as a train, that force is magnified hugely. The heavier the train, the greater the inertial resistance, whether it's starting, stopping, or changing speed. It's a basic principle of physics, but so important to train dynamics.
Fascinating. So we've talked about all these forces working against a train, but how does a train actually generate the force to move forward and overcome all of that resistance? I mean, it doesn't just magically glide along the tracks.
You're right. There's a vital force at play here, and that's adhesion. This is what stops those wheels just spinning on the tracks.
Okay.
Think of it like the grip between your shoe and the ground. Without that, you'd be able to walk. Same with the train. No adhesion, no movement.
So it's the adhesion between the wheel and the rail that actually makes the train move forward.
Precisely. It's all about that contact point between the steel wheel and the steel rail. The force that the train's engine transmits to the wheels to propel it forward, we call that traction force. And just like those resistance forces, various factors can affect how much traction a train can generate.
So all those things we talked about, like rain or leaves on the track, those things can also impact a train's ability to generate traction and actually move forward.
Exactly. It's all a balancing act.
Yeah.
Engineers put a lot of work into optimizing a train's design, its weight, its power, even the shape of its nose, all to maximize traction and overcome those resistances we've been talking about.
It's amazing how much thought goes into every single aspect of a train's design, all to overcome these forces we probably never even think about when we see a train go by.
It really is a testament to human ingenuity and our understanding of physics, that's for sure.
It is. Our sources also mention that different types of train, for example, diesel versus electric, have different traction characteristics. What makes them different in terms of how they generate that pulling power?
Good question. And it just goes to show that even within the world of trains, there are so many different approaches to this. Electric trains, for example, they typically have better traction at lower speeds. This makes them much better suited to urban environments, where they're frequently stopping and starting. Diesel engines, on the other hand, they tend to perform better at higher speeds, making them more suited to those long-haul journeys over vast distances.
So choosing the right type of train for a route for its purpose isn't as simple as just speed and power. It's about understanding the nuances of how they generate that all-important traction force. Fascinating.
Exactly. All these factors play a part in designing efficient and effective rail systems.
This has been so interesting, such an eye-opener. It's incredible how much science and engineering goes into something that we just take for granted. Seeing a train go by will never be the same.
Glad you've enjoyed it. It is exciting to delve into the details and see the complexity behind these everyday things.
Absolutely. So we've covered a lot today, all about braking systems and those forces working against trains every single day. Before we wrap things up, one final question for you. We've seen some massive advancements in train technology over the years, from high-speed rail to regenerative braking. So what does the future hold for train travel? What new innovations are on the horizon that might reduce resistance even further, increase energy efficiency, just make rail travel even smoother and more sustainable?
That's the question.
Yeah.
The world of train technology is constantly evolving, and researchers are always pushing the boundaries. They're exploring things like using new materials that reduce friction, innovative aerodynamic designs to minimize air resistance. The possibilities are endless.
It's exciting to think about, isn't it?
It is.
Well, on that note, we'll leave you to ponder the future of train travel. This has been a truly enlightening deep dive.
It has. Until next time.
And to all our listeners, keep those wheels turning. We'll catch you on our next adventure into the world of knowledge. It really makes you think about the future of train travel, doesn't it?
Sure.
All those possibilities. But for now, I think we've done a pretty good job of unpacking the world of train braking and all those resistance forces.
We've covered a lot, that's for sure.
We have. Before we finish up for today, though, something to think about. We've talked about adhesion, that force that's vital to allow trains to move. Well, it made me wonder, are there limits on how much a train can pull? I mean, does adhesion ever become a factor in how trains are designed and operated?
That's a really interesting point, and you've hit upon a really important constraint in train engineering. Because, yes, adhesion does impose limits. There's only so much force those wheels can put down on the rails before they start to slip, and that's especially true in difficult conditions, like when it's been raining or snowing.
Right, so like when you're driving your car on an icy road, you only have so much grip.
Perfect analogy.
Sure.
And just like you might put snow tires on your car in winter, engineers are constantly having to come up with new technologies and strategies to maximize adhesion for trains.
Like what?
Well, they use things like sand to increase the friction on the tracks, optimize how the weight of the train is distributed, even experiment with new materials for the wheels and rails.
Wow, so it's a constant effort to overcome these challenges that are basically just down to physics.
Exactly. And it's this drive for improvement that makes the world of train engineering so fascinating.
Yeah.
There's always a new challenge to solve.
It sounds it. Well, on that note, I think we'll leave our listeners to contemplate the limits and the possibilities of adhesion in the world of train travel. This has been a truly fascinating deep dive.
It really has.
It has indeed. And to all our listeners, until next time, keep those wheels turning. We'll catch you on our next adventure into the world of knowledge.